everyone, I'm Dan Fullerton, and in this video what we're going to do is take the 2015 AP Physics 1 free response questions and see if we can't go through those to do our best to come up with at least a first pass of what solutions would look like to those problems. Having said that, I haven't seen the official solutions or scoring guide yet, so quite possible there's a small error or two in here as we go through it, but maybe you'll at least get a good idea of what they're looking for and how you might go about answering some of these questions. Secondly, because there is so much writing on the AP Physics 1 exam, instead of having you guys watch me write out my answers to all of these, when we get to the answers that are asking you to write a paragraph, things like that, I'm just going to highlight the key points that I would expect to see in an answer. So, with that, why don't we take a moment and we'll dive into question number 1. Alright, so in question 1, we have a couple blocks hanging from a table with some massless pulleys by a string. Alright, we've got some dots here and it wants us to draw free body diagrams for each of our blocks. Well, the way I would start that is we look over here at A. For block 1, we have the tension in the string up and its weight M1G. And I would expect that we would see T slightly bigger than M1G. For block 2, we will have the same tension, but M2G will be larger than T. So over here, M1G and T is just a little bit larger than M1G. Over here, same tension, M2G significantly bigger than T. So that would be my free body diagram. Now for part B, derive the magnitude of the acceleration of block 2. Alright, well for that I'm going to go to Newton's second law in the y direction, and I'm going to look over here and say, you know what, I think the whole thing is going to be going in that direction. So I'm going to call that my plus y direction. So looking at block 2 first, I would write my forces in the y direction. We have M2G minus tension must equal mass times acceleration, M2A. Now as I look over here at block 1 as well though, now I have T in the positive y direction as I've defined it. So T minus M1G equals M1A. And with just a little bit of rearrangement, I can write that to say that T is equal to M1G plus M1A. I can now take this T and substitute into that equation to get an equation where we don't have to worry about the tension anymore. So when I put that together, I come up with M2G minus what I have over here for T, M1G minus M1A equal to M2A. And again, a little bit more algebra here. This implies then that, let's see, M2 minus M1 times G equals M1 plus M2 times A. Or with just a little bit more rearrangement, I could say that A then, our acceleration, what we're solving for, is going to be equal to M2 minus M1 over M1 plus M2 all times our acceleration due to gravity, g. So that would be a reasonable answer, I think, for part B. All right, now as we look on to C, we're adding this block 3 in the middle. And there's no friction between block 3 and the table. We're now supposed to state whether the acceleration of block 2 is larger, smaller, or the same as in the original 2-block system, and how we arrived at that answer. Well, the way I would look at this, and of course you would put this in some sort of paragraph format, write it out, is that the acceleration of block 2 is now smaller. Why? Because in this new system, the net force on the 3-block system is unchanged. We still have the net force from M1 and M2 in those opposite directions, the force of gravity on those 2 blocks. But the mass of the system is larger. So same force, larger mass, Newton's second law says we're going to get a smaller acceleration. So I would explain something to that effect, and that would close out number 1. All right, let's take a quick break. We'll come back to question number 2. Number 2, a circuits question. Some students want to know what gets used up in an incandescent light bulb when it is in series with the resistor, current, energy, or both, and they come up with a couple questions. They want to know if fewer electrons leave the bulb than enter the bulb, and they want to know, does the electric potential energy of electrons change while inside the bulb? Now, realizing you probably already know the answer to those questions, that's not really what it's asking. Instead, it gives you a list of equipment and wants you to describe an experimental procedure that you could use in order to answer those. So state the measurements you would make, how you would use the equipment to make those measurements, and a nice, neat labeled diagram of your setup. So for part A, what I would do is I would look at a series circuit in which we have two ammeters flanking the light bulb that we're building. So for part A, my diagram, let's give ourselves a power supply, and I'm going to throw a resistor in here just to help limit the current. Theoretically, you probably don't need it. Practically, it's not a bad idea to help keep you from having an unlimited current if something happens to your light bulb. So we'll throw that in there. We'll come over here and we'll put our light bulb. And there's a functioning series circuit with our light bulb in it. Now, to measure the number of electrons leaving and entering the bulb, well, what I would probably do there is let's put an ammeter on either side of our light bulb. Now we can measure the current going in and the current going out. All right, so that would work. And the other thing that I would probably look at is a voltmeter in parallel across the light bulb. So we'll put our voltmeter right over there. All right, now what I would do is probably something like set the power supply to about 5 volts and measure the current entering and leaving the circuit through our 2 ammeters. And of course, we're going to find out that that current's the same when we actually do it. And I would repeat that for different voltages from 0 to 5 volts, maybe starting at 0 volts, 1, 2, 3, 4, and 5 volts, and recording the current in, the current out, the voltmeter reading, and the power supply setting. So by having the electric potential difference across that lamp, we would also be able to answer the question, does the electric potential energy of electrons change while inside the bulb? If we have any appreciable voltage there, electric potential difference on either side of the bulb, we know those electrons must have a different electric potential energy to answer that question number 2. So that's how I would go about explaining number A. Now for B, it says, explain how the data could be used to answer those 2 questions. And I think I did that a little bit, but just to reiterate, if the current readings into and out of the bulb are the same, then that means that the same amount of electrons must be leaving the bulb as enter the bulb. That answers question 1. And about the electric potential energy difference across the light bulb, well, that'll be our voltage reading across the light bulb. If this is non-zero, then we know the electric potential energy is changing inside the light bulb. So something like that in a sentence or 2 ought to do it. All right, now things get a little funky. A light bulb is non-ohmic if its resistance changes as a function of current. Does it follow Ohm's law? If yes, it's ohmic. If it doesn't, it's non-ohmic. Your setup from part A is to be used or modified to determine whether the light bulb is non-ohmic. So trying to find out, does it follow Ohm's law or not? How, if at all, does the setup need to be modified, and what additional data would need to be collected? Well, to answer that, I think we've got all the data we need with our current setup, so I would say we do not need to change our setup at all, nor do we need to collect additional data. But how would we analyze that data in part D? Well, I would make a plot of voltage across the bulb versus current. When we do that, if the bulb is ohmic, we would expect to get a linear plot. If it's non-ohmic, the plot would not be linear. So uncertainty in the power supply, as well as the electrical meters, could lead to a graph that's not completely linear, with some variation from the best fit line. And if the uncertainties in those measurements in the meters is too large, well, at that point, it may not be reasonable to differentiate between a straight line, an ohmic bulb, and a nonlinear plot, the non-ohmic bulb. So really, when we talk about uncertainty, it comes back to how close can we measure to see whether this is linear or not. So that's how I would answer number 2. Again, probably take you a little bit longer to write that out in words than it does for me to explain it verbally here, but I think you get the idea, the general gist of the question. All right, let's take a quick break and we'll come back to number 3. Next up, question number 3. Now we have a block with the spring on this table, and the block's initially at position 0, and it's in contact with that uncompressed spring, the block is pushed back along a frictionless surface to x equals minus d, so it's compressed some amount d, and then it's released. When it gets back to x equals 0, it enters a rough part of the track, so we're going to start to have some friction come into play. It comes to rest when it gets to x equals 3d, and the coefficient of kinetic friction between that block and the track is mu. So, A, on the axes below, sketch and label graphs of the following two quantities as a function of the position between negative d and 3d. And we're looking at the potential energy, K, of the block and the potential energy of the block spring system. So first thing I'm going to do is make my plot. Okay, so now we have our axes made. Let's see here. When we're at negative d, all of the energy is stored elastic potential energy. So I would probably come up here and make that our maximum for our elastic potential energy, and it's not moving at all, so kinetic energy at that point is going to be 0. So there's our kinetic energy. Now when we get to x equals 0, the elastic potential energy is 0. Let me do kinetic energy in a different color here just to differentiate it. And we have our maximum kinetic energy. And let's make that U just a little bit cleaner, help highlight that it's right up here at the same point. Oh, I'm having trouble with colors today. There we go. All right, so, and the total mechanical energy at this point must remain constant. We're not losing anything to friction. So I would probably plot something kind of like this for our region from negative d. And we'll make that a little prettier maybe. From negative d down to 0. From 0 forward, the spring isn't compressed anymore, so there's no elastic potential energy, but our kinetic energy is going to decline until we get to 0 speed at x equals 3d. So our kinetic energy now is just going to be a line from 0 to 3d. How do I know it's linear? Well, the force of friction in here is going to be constant, so the work done by friction, force times displacement, is a function of x. That's just going to be at a constant rate with respect to distance. We're going to be losing at a, so that's going to give us a straight line is the short version. So my graph would kind of look like that, something in that general realm. So that answers 3A. Now let's take a look at 3b. The spring is now compressed twice as much to x equals 2d. All right, the student is asked to predict whether the final position of the block will be twice as far at x equals 60. Student reasons the spring will be compressed twice as much. The block will have more energy when it leaves the spring, so it'll slide farther along the track before stopping at x equals 60. Which aspect of the student's reasoning are correct? Explain, and which are incorrect and explain. All right, well, I would start by saying the student is correct in that the spring will be compressed twice as much as before, and the block will therefore have more energy when it's compressed and more energy when it's released. So it'll slide further along the track. Now, the student is incorrect in stating the block will stop at x equals 60, though. Doubling the spring's compression quadruples the elastic potential energy. The elastic potential energy stored in a compressed spring is 1/2 K times the displacement from equilibrium position squared. So if we double that distance, we quadruple the energy stored there. So I would expect it to go 4 times as far and stop at x equals 12d. So that's how I would answer B. C says using quantitative reasoning, including equations as needed, develop an expression for the new final position of the block. Express that in terms of d. So qualitatively, we've already understood that that's probably going to be at 12d, but let's prove it mathematically. Well, the stored potential energy in the spring is 1/2 kx squared, but now we're going from x to 2x, so our new elastic potential energy when we're doubling x is going to give us 4 times our initial stored elastic potential energy. So our new kinetic energy when we get to x equals 0 is going to be 4 times what it was initially, 4 times our initial elastic potential energy, which means we're going to get 4 times the work done, which means we have 4 times the force times distance, the initial distance, which is going to be 4 times the force, which occurs when we have 3 times the distance. Oops, I should probably make that a capital D. 4 times 3D, which is going to be 12 FD, which implies that our new distance traveled is going to be 12D. It's going to go 4 times as far. So some sort of quantitative reasoning like that. And there are bunches of ways you could explain that, lots of correct ways to do it. Really depends on how you're thinking and how you like to justify these. But I think you're going to come up with a new distance of 12D, which is 4 times as far as it went initially. And Part D, explain how any correct aspects of the student's reasoning identified in Part B are expressed by the mathematical relationships in C, and how the relationships in C correct any incorrect aspects of the reasoning in Part B. Refer to the relationships you wrote in Part C, not just the final answer you obtained. Oh my goodness. That's an awfully confusing question with lots of loopbacks previously. I think what they're trying to get at is explaining, based on your previous answers, what you came up with and justifying that. So what I would put here is something to the effect of the correct reasoning is expressed in Part C by indicating the compressional distance is doubled, therefore the new elastic potential energy is greater than the initial elastic potential energy, and the final x value is greater than the initial x value. The relationship that the new distance equals 12D, 12 capital D, 4 times the initial distance, corrects the student's incorrect reasoning from Part B. And I think that covers what they're looking for. But again, a lot of that is a question in how you're reading as opposed to what you're really seeing going on here. So, I think that finishes question 3. Or if it doesn't finish question 3, that's probably where I'd stop and at least go on to the next question. Because that Part D, there's a lot of trickiness in there and relating back to previous problems. I think we've got most of our points. Let's move on. Number 4, a projectile problem, a sphere that's dropped and one that's projected horizontally. Fairly common demonstration in physics. Our 2 identical spheres are released from time t equals 0 from the same height, capital H. Sphere A drops straight down. Sphere B is given a horizontal velocity v0, and it travels some horizontal distance, capital D, before it hits the ground. We're going to neglect air resistance, draw free body diagrams showing and labeling the forces on each sphere at time tf over 2, halfway between when they are launched and when they hit the ground, so while they're in the air. So sphere A has the force mg, the force of gravity on it, or you could label that F sub g, however you like to write gravity. Sphere B has the exact same force. Free fall, projectile motion, the only force acting on these objects is gravity, so we would have the same free body diagrams. Pretty straightforward there. Now, on the axes below, sketch and label a graph of the horizontal component of the velocity of sphere A and sphere B as a function of time. The horizontal component of velocity, well, this should be a pretty straightforward graph. I'm just going to sketch it in very quickly here. Function of time, we've got the horizontal component of velocity here. And I would probably use a ruler just to make sure you're very careful, but sphere B is going to be constant. There's B, starting at v0, its initial speed in the x direction. Sphere A, the entire time, has no velocity horizontally, so there's A. It just sits there at 0. So a fairly straightforward question there for B. Now C, another one of these writing questions. In a clear, coherent, paragraph-length response, explain why the spheres reach the ground at the same time, even though they travel different distances. Include references to your answers to parts A and B. So before I actually start writing a paragraph, I would probably outline this out. Make sure that you have a topic sentence, a couple supporting sentences, and know where you're going. Quickly outline it, and then write up your paragraph length response. I would probably put something sort of like this. The spheres reach the ground at the same time, even though they travel different distances due to the independence of the sphere's horizontal and vertical motion. As shown in the free body diagram in Part A, the only force on the spheres is the force of gravity downward, which is the same on both spheres, resulting in the same downward acceleration. Though sphere A has 0 horizontal velocity and sphere B has a constant horizontal velocity of v0 as shown in the graph in Part B, their vertical velocities will be the same at all points in time. Both spheres start with an initial vertical velocity of 0, and both accelerate downward at the same 9.8 meters per second squared. They both travel the same vertical distance with the same vertical acceleration and the same vertical initial velocity, 0. Therefore, we can apply the kinematic equation for cases of constant acceleration to show that they spend the same amount of time in the air, and therefore they reach the ground at the same time. Mathematically, I would write that as the displacement in the y direction is v0 t plus 1/2 a t squared. And we're really looking in the y direction, so that's y. That's sub y. And this implies then, since our initial velocity in the y direction equals 0, that t equals the square root of 2 delta y over ay. They both have the same vertical displacement. They both have the same vertical acceleration. Therefore, they are both going to be in the air the same amount of time. All right, a lengthy response. You're probably going to spend most of your time in this question writing. The actual physics, pretty straightforward. The explanation of the answer in that paragraph length response, a little bit trickier. That finishes up number 4. Got one more to go. Number 5. I thought this was a pretty interesting question. I haven't seen something quite like this before. We have a string with one end attached to an oscillator and the other end attached to a block, and the string passes over a massless pulley with no friction. We have 4 of those set up side by side on a table, and the oscillator is adjusted to vibrate the string at its fundamental frequency, f in each case. The distance between each oscillator and pulley, L, is the same, and the mass of each block, M, is the same, but the fundamental frequency of each string is different. So it also gives us the equation for the velocity v of a wave on a string. V equals the tensional force divided by the mass per unit length square root. So tension in the string, mass per unit length, or linear mass density of the string. And something to be careful of, we're using m over L for linear mass density. Sometimes in problems we use lambda to talk about linear mass density. In this case, since we're talking about waves, let's keep lambda solely to talk about wavelength. Anytime we're dealing with linear mass density, let's leave it as m over L, just to help with our notation. So part A, what is different about the 4 strings that would allow them to have different fundamental frequencies? Explain your answer. Well, when I look at that, I'd say since the wavelengths are constrained by the geometric proportions on the table, they all have the same L. The only way that happens, if they all have nearly the same tension too, because they have the same massive blocks hung on the end, they must have a different mass per unit length. They must have a different thickness, mass thickness for each string. So the big shift here must be the difference in the strings, the mass of each string. Therefore, you get a shift in the wave speed per the given velocity of a wave on the string equation. V equals F lambda. So the short answer to A, M over L must be different for each string. And of course, explain that in a little more detail, even if I talked in a circle there. Now, for B, a student graph's frequency is a function of the inverse of the linear mass density. Will the graph be linear? And how did you arrive at that answer? Now, I would not expect a linear graph of frequency versus the inverse of linear mass density. Wave speed is the product of frequency and wavelength. So as we're looking at B, V equals F lambda. But V, we just said, is the square root of the tension divided by the mass per unit length of the string, which is equal to F lambda. What I'm going to do is try and get this as a function of 1 over m over L, the inverse of the mass per unit length. So I'm going to square both sides here and say that F squared, wavelength squared, equals tension divided by m over L. And let's rearrange this a little more to put it in a form that might be more useful for graphing. I would then say if we wanted to graph the square of frequency, F squared would be equal to the tension divided by our wavelength squared times 1 over m over L. So if we were putting this in the equation of a line, this would look something like y equals mx, where our y-axis would be the square of frequency, our x-axis we would graph the inverse of mass per length, and our slope would be the tension divided by the square of wavelength. So I would expect frequency squared versus the inverse of mass over length to give us a linear relationship, not frequency versus mass over length. And if you explain that in words, and probably worthwhile showing this derivation, that you have this in a form that's linearized to get full credit on a question like that. All right, and on to part C. The frequency of the oscillator is changed so the string vibrates in its second harmonic. On the side view, mark and label the points on the string that have the greatest average vertical speed. All right, I'm going to give us a new page here to help diagram this out. But the way I would look at this is, let's say we have our table here. We have our oscillator, and over here we have our pulley with a mass, our block, sitting on it. Well, the trick here is recognizing that at the second harmonic, our length, L, is equal to the wavelength of our string. So just drawing the standing wave we might obtain in a question like this, in one position, I would recognize that we probably have a node here, a node there, and a node over here. So if I were diagramming this, I would say at any specific instant in time, our wave probably looks like that. So we're looking for the points that are antinodes, where the string is going to have the greatest vertical speed. That occurs there and there. Those points are going to move with maximum amplitude for the same amount of time and have the greatest speed. So I would label those as the antinodes. And those would be the two places where I would expect that we would have the greatest average vertical speed. And it looks like that finishes the free response portion of the exam. Hopefully that gave you a little bit of help on these problems. Thank you so much for your time, and have a great day, everybody. If you need more help, check us out at aplusphysics.com.